Okay, so by just discussing studying the consequence of Newton's third law, we have discovered some other conserved quantity, this momentum. Now, the next thing that we will be doing, of course, is how can we use this conservation law? Okay, in the case of the energy conservation, we could study let's say, for example, the roller coaster. That was an application. Now, we will be eventually going to the applications of the conservation of momentum after we discuss a few more definitions. But before we continue, do you have any questions on this one? Now, the critical thing is the force we can also describe as the change of momentum, the rate of change of momentum, how much momentum of an object changes in a given time. Now, action-reaction pairs just tells me that if an object is gaining momentum due to their internal forces, the forces that they exert on each other, if one is gaining momentum, the other one should be losing momentum. So that is another way of expressing Newton's third law. But if one is gaining momentum, the other one is losing momentum, then the sum of the momentum is not changing. That is basically what the conservation of momentum means. Of course, if there are some external forces acting on the system, in that case, the total momentum of the system will change depending on the external forces acting on the system. Now, this is independent of what our system is, in the sense that, okay, we have we can just take these point particles, we can consider all of these point particles as our system. Of course, these point particles can be changing their relative position, so they can be the atoms in a gas, or the atoms in a solid in which the atoms will not move relative to each other. They can be liquids, you can take the sun and the earth as your system, etc. Whatever your system is, whatever the changes in your system are, the total momentum of your system will only change if there are external forces. There are forces that are caused by objects that are not in your system exist. It's quite general. It is valid in every case. Any question? And the nice thing about this conservation of momentum is independent of the nature of the forces. As long as they satisfy Newton's third law, they should conserve the momentum. Now, let's look at this equation. Now, we just said that this is quite similar to Newton's second law for extended objects. This is quite similar to F is equal to dP by dt. But in this case, the momentum, we had a nice definition of the momentum. The momentum was equal to the mass of the object times the velocity of the object. Now, if we have an extended object and different parts can be moving in different directions, we cannot, this momentum over here, we cannot really say that it is some mass times the velocity of one part of the object. But what we can still do is that we can define this P, the large P. This is just the definition as the m times v center of mass. This is definition. This is m is the total mass of the system. So m is nothing but sum of the masses of the objects making my system. So in the case of these two particles, the particle example that we had been discussing here, it is just m1 plus m2. And the velocity of the center of mass, now the Cm is center of mass. Again, it's just a definition. Why do we call the center of mass will be apparent in a moment. And the velocity of the center of mass, we can just write as 1 over m times the total momentum of the system, which will be 1 over the total mass times sum over the momenta making the system, of each one of the particles making the system. Again, these are just definitions. We have We have a bunch of different point particles. They can each be moving in different directions. I can talk about the total momentum of my system, and the total momentum is nothing but the sum of the individual momenta. And then this total momentum, I just want to write it as if it was a point object. Although it's not a point object, I just want to write the total momentum of the object as if it was a point object, in the sense that it is the total mass of the object times some velocity. Now this defined velocity is what we mean. We define it like this. This is what we call the velocity of the center of mass. So for example, if you have, let's say, one-dimensional motion, I have some mass m moving in this direction with speed v0. The other one, let's say, moving in the same direction at exactly the same mass, which has a speed, let's say, 2v0. In that case, the total momentum of my system will be m times v0 plus m times 2v0, 3m times v0. And the total mass of my system will be m plus m. It is 2m. And the center of mass velocity will be p over m, which is 3m v0 divided by 2m, or 3 over 2 v0. It will be moving with the speed. I can, of course, define the acceleration of the center of mass as the rate of change of the velocity of the center of mass. In this case, what we had proven is that the total external force is nothing but the total mass of the object times the acceleration of the center of mass. Again, in this expression, the acceleration of the center of mass depends only on the total external force. It doesn't depend on the internal forces, the forces that one part of my system is exerting on the other part of the system. It doesn't depend on what kind of motion my system is making. It doesn't depend on whether my system is changing shape or moving without changing its orientation or shape. The acceleration of the center of mass only and only depends on the total external force acting on my system. Now, looking at this system, we had defined the acceleration, we had defined the velocity. We can also define some kind of a position. Where is my center of mass? Well, you see, the velocity of the center of mass, we can define it as the r of center of mass divided by dt. Now, if we remember the definition of the velocity of the center of mass. We had said that this is 1 over m times sum over the momentum of each particle making my system. That is mi times vi, which is 1 over m mi times, well, the velocity of a particle is nothing but the rate of change of its position. One over m times, well, the derivative, I can just put this constant inside. Well, the derivative, the sum of the derivatives is nothing but the derivative of the sum, and this is just a constant, so this is nothing but d by dt of 1 over m mi/ri. This is the position of the center of mass. So in a sense, what we are actually doing is, although we can have this expanded large object, it can be some gas constantly changing its shape, it can be this book, etc. We can describe its motion, at least its linear motion, as the motion of just a single point that we call the center of mass of the object. We define its velocity. The velocity is nothing but the rate of change of the center of mass of the object. Then we can talk about the acceleration. Acceleration is nothing but the rate of change of the center of mass velocity of the system. And then the acceleration of the object. The acceleration of the object is determined only and only by the external forces acting on my object. This is independent, I repeat, this is independent of whether my object is changing its shape, whether it is changing its volume, whether it is rolling or non-rolling, or just you can think of whatever it does. The acceleration of the center of mass only and only depends on the total external force acting on the system. Yes, question?
Next page. Is it R3?
Well, let me write it in a more clear way. Well, in a sense, the position of the center of mass is a kind of an average of the positions of parts making my system. So if M1 is equal to M2 is equal to M, just like our previous example, then the total mass will be 2M. The position of the center of mass will be equal to 1 over 2M, M1 times R1, or M times R1, plus M times R2. So this will be equal to 1 over 2 R1 plus R2. Or if we go back to our previous example, so these were the two objects of identical masses. So this is the line connecting them. So this is where the center of mass is, just in the middle. In the middle because they are equal masses. Now you see the center of mass, by the way, doesn't coincide with any mass. It's just in vacuum. There's nothing over there. It doesn't have to be on one of the masses.
When can the internal forces have some effect of the acceleration?
Some?
Effect, I mean, when they can cause acceleration.
Now the internal forces might cause different parts to accelerate differently. But that effect will not change the acceleration of the center of mass. Internal forces will never affect the acceleration of the center of mass. Now, if you go back to the previous case, now this is the two-body example. You see, there are these internal forces. Okay, there are, well, now let's go to the previous one. Let's forget about the external forces for the time being. If you look at this example, this mass M1 is accelerating in that direction. This other mass M2 is accelerating in that direction. So it's the internal forces causes these two masses to accelerate in different directions. But it doesn't affect the acceleration of the center of mass. Other questions?
Please change the... I'm right.
No, sorry. Which one? This one. Well, this is an old slide. The last one. This is the last one. Oh, you will be receiving these PDFs. You can just copy them.
You are talking about about velocity of center of mass. But the objects are far and then they explode.
Now, you see, we are not really specifying the nature of the force. There can be any force. As long as they can exert a force on each other, this will be true. One case will be you have these two objects, you throw them to each other, and then they will hit each other, and then they will change their direction of the motion.
The center of mass is changed after they.
Well, is there an external force? If there is no external force, then the center of mass acceleration is zero. Whatever happens inside. I mean, you can have an object, it can explode, divide into 1,000 different particles, each moving in different directions. If there are no external forces, the center of mass does not accelerate.
There are two objects, they are going this way, and when they are together, the center of mass is changed.
No. And the definitions are always this one. Of course, for example, you have this object is moving, the center of mass is some point in between, so it also has some velocity. When they hit them, they will keep moving. The center of mass is still some point in between. And if there are no external forces, the center of mass, acceleration of the center of mass will be zero, so the center of mass will move at constant velocity. Let's do an example. You have this platform on wheels, and you are standing over here. And suppose that you move 1 meter. Let's say you move 1 meter. So you are here, you come to this point, and that distance is 1 meter. And then there's your friend looking at you. According to your friend, how much did you move? Let's say that your mass is m, and the mass of the cart is also m. So first of all, does the cart move at all? I mean, if the cart is at rest, then if the man is moving 1 meter like this, then your friend will see that you are also moved by 1 meter. The cart doesn't move. It moves backwards. The center of mass will change. It doesn't change. So will the center of mass change? The position of the center of mass, will it change? Will it stay the same? Change. How many of you think that it will change? The position of the center of mass will change. How many of you think that the position of the center of mass will not change? Okay, why do you think it will change? Okay, so you are saying that the man will just move over here, the cart doesn't move, so as a result, some of the masses change their position, so the center of mass will change its position. You don't know it will change, but then how do you say that the center of mass will change? Because if the man is moving towards the right, the cart moves towards the left, so then the center of mass might still be constant. We don't know the speed. I mean, it can be even accelerated, stopping down. He might have just come to this edge and then came back over here. We don't know. But
wouldn't move that direction with the speed that you move that direction. Does the speed of you relative to the car will be different to the system speed?
So what do you mean by system speed? The speed of the center of mass?
No, the man and the car together.
Okay, so what does it mean? You see, we talk about the speed of point objects. This is a large object. So we cannot use that definition. We define the speed of the center of mass. Now, before we were talking about when we had such large objects, we just chose one arbitrary point and said that that is the speed of the object. Now we see that that arbitrary point is in fact has to be the center of mass. Are you talking about the speed of some point over here, the speed of the center of mass, speed of the guy? Okay, the center of mass. What is the change in the speed of the center of mass?
The man's center of mass or system?
Well, you're telling me. We can talk about the center of mass of the guy, the center of mass of the card, or the center of mass of the whole system.
My point of view, if you want to move to that, the car has to move to backwards because of the conservation of the momentum.
So how is that related?
So,
How is the conservation of momentum related with the fact that the car should move in that direction?
because you are moving with the speed, thus you are having momentum in that direction. So you are applying the momentum in the system, but the system's momentum must be conserved. So the whole system must move backwards.
So that the total momentum will be zero all the time.
Yes.
Well, in fact, that's kind of the answer also what happens to the center of mass. The total momentum of the system is zero. Initially, it's not moving. So there are no external forces acting on the system. So if there are no external forces acting on the system, the momentum of the center of mass should be the same, should remain the same. It should not change. The momentum of the center of mass should always be zero. If the momentum of the center of mass is always zero, that means the acceleration of the center of mass is always zero. But if the acceleration of the center of mass is always zero, that means the center of mass is not moving. The center of mass should always be here. Well, that is one point of view from the perspective of the momentum conservation. How can we explain this using forces? So you have, if the center of mass is constant, that means if some mass moves in this direction, some other mass should be moving in the opposite direction, so that the center of mass will always stay the same. But what causes the cart to move?
What we are moving towards the right side, the exert force towards the left side.
What is that force?
Friction.
Friction force. I mean, you see, up to now we have been discussing the friction force acting on us when we are moving forward. We said that if you are accelerating forward, let's say, at that instant there is it is the friction force that is causing you to accelerate in this direction. So the friction force acting on you by Earth is in that direction. So if this guy, from that point on, he starts moving towards the right, that means there is a friction force acting on the guy at this instant at least, which is towards the right. But that also means, again, remember Newton's third law, there is a friction force acting on the cart. The man is exerting a friction force on the cart, which should be in opposite direction and of the same magnitude. So this is due to the Newton's third law. So as the guy is moving in that direction, the cart is moving in the opposite direction. Now this is true at every instant. For example, the static friction force, its magnitude can be changing in time depending on your acceleration, or the guy might just move in this direction and then come back and then go back in that direction, etc. But at every instant, we know that there will be a force acting on the guy if he's accelerating, and there will be an opposite force acting on the cart, of course, if the man is accelerating. So this is why, as the guy is moving towards the right, the cart will be moving towards the left. But now there's one more question. What is the displacement of the man? according to this observer. Yes.
I was going to ask.
You can ask questions.
There is only friction force reaction here of the friction force on the knife. On car, there is no friction force.
There are only friction forces acting on the different parts.
So if there is only one force, I think the net force is zero.
True.
So car is moving the left side.
Okay.
There is no opposite motion, so it will go accelerate. It will accelerate towards the left.
The cart.
Yeah.
Okay.
It will go and go. It won't stop.
Well, let's see. Let's study the motion. Let's just imagine I'm just standing over here. I'm on a cart. And I will just make a simple motion. I will just move in that direction and come here and stop here. This will be the motion. I'm at my initial position. Now I'm accelerating in that direction, initially. I will be moving. I have zero velocity. I have some finite velocity in that direction, so I'm accelerating in towards your right. So what is the direction of the force acting on me? In that, I'm accelerating in that direction, so the force acting on me is in that direction. What is the direction of the force acting on the cart? In the opposite direction. They are action-reaction pairs. So the cart will be accelerating in that direction. Now I'm moving. I accelerated, I move at constant velocity, and then I stop. What is the direction of my acceleration? I had some constant velocity at some time, and then at the final time I stopped. What is the direction of my acceleration? Average acceleration in that direction. What is the direction of the force acting on me? What is the direction of the force acting on the cart? In the opposite direction. So if you don't follow my motion, but the motion of the cart, we are all at rest. I'm moving towards the left. The cart is towards the right. The cart is moving towards your left. Then I stop, and the cart stops. So as I am stopping, I am also exerting a force on the cart to stop that one too. Yes. If I keep on moving, then the cart will also keep on moving. But if I want to stop, there has to be something exerting a force on me. I cannot exert that on myself. That's an internal force. It's the cart that will be exerting a force on me. But that means I'm exerting a force on the cart to stop. You see, there is no friction between... the reason why the cart stops is not the friction with the ground. It is the friction between me and the cart. The reason why I wrote that there is no friction between the cart and the ground is that if there was some friction between the cart and the ground, that would be an external force acting on my system. In that case, then there might have been some shift in the center of mass, because there's an external force which will cause the acceleration of the center of mass, which will cause the center of mass will be displaced. Because there is no friction between the ground and the cart, the center of mass should always be at rest. The cart stops because of the force that I exert on it, not because of the external friction.
Because of previous stage, we show that can we say the displacement is zero? Displacement of me is zero.
What is zero?
Displacement.
Your displacement. Why should it be?
Because go right direction 1 meter and cart go for opposite.
1 meter or less? How do you know that it's 1 meter? Now, if I move on the cart 1 meter in that direction on the cart, if the cart moved 1 meter in the opposite direction, then my displacement would have been zero, because I would move relative to the cart, I would move 1 meter, but the cart had carried me on the other opposite direction 1 meter, I wouldn't have been displaced. But is it 1 meter? How much will be the cart displaced? How can we show it? Let's see what we already know. Let's use what we already know. We know that the change, what's the position of the center of mass? Position of the center. Let's write it in terms of the position of my position and the cart's position, the definition of the center of mass. It is 1/2 Well, 1 over 2 basically because I just assume the masses to be equal. R1 plus R2. This is the position of the center of mass. R1 is my position, R2 is the position of the cart. Well, of course, when I'm talking about my position, I have to pick one point on my body, and that would be my position. And when I'm talking about the position of the cart, I have to pick one point on the cart to represent the position of the cart. Now, the change in the position of the center of mass, we had just said that since there are no external forces, because there is no friction, external friction acting on my system, in that case, the change in the position of the center of mass will be 0. But the change in the position of the center of mass is 1 over 2 times delta R1 plus delta R2. That means that delta R1 should be equal to minus delta R2. Of course, remember, this is relative to an outside observer. There I am on the cart and you are looking at me. What you will see is that if I move towards the left by half a meter, you will see that the cart will move towards the right by half a meter. Again, this still doesn't answer my question. How much did the car move? I just moved 1 meter on the cart. I was at this point, then I moved to this point, which is 1 meter away from the initial point. Question?
Can you again see the last sentence?
This one.
Yes.
We started from here, the definition of the center of mass. Well, since the masses are equal, the center of mass is nothing but the average position of the two objects. I know that the center of mass doesn't change. But the change in the position of the center of mass, which should be 0, is nothing but half the changes in the position of my objects. So this sum should be 0. If that sum is 0, delta R1 and delta R2, the displacement, my displacement and the displacement of the cart, they should have equal magnitudes and opposite directions. So that the sum will just be 0. Now let's calculate how, yes, question. Okay.
I think it's half of it.
How do you obtain that?
Because the displacement relative to the car should be 1 meter. So
Okay, so let's write it in this way. This is the initial position of the car. R1 initial. Now R2 initial. I also, let's say that I'm also staying at the point, it's also equal to R2 initial. This is the initial state. Now R1 initial is the position of this mark. Well, I can just choose any point on the car to specify its position. Now then I move, I come here, this is R1 final. Then the car also moves here, it comes here, this is R2 final. This distance over here is 1 meter. Well, just as your friend has pointed out before, I can just choose my origin to be here. X. So that R1 initial is equal to R2 initial, this is equal to 0. It's one-dimensional motion, so I can say that R1 final minus R2 final, this length is also 0. Now I can just say, write the one-dimensional components. But I also know that R1 final plus R2 final. No, sorry, this is 1 meter. This is 1 meter. R1 final plus R2 final, which is nothing but delta R1 plus delta R2. This should be equal to 0. Now this is just a statement that this is my relative position relative to an observer on the cart. And we know that we are told that my relative displacement on the cart is 1 meter. We had also derived that the center of mass doesn't change. So this is the change in the center of mass, this delta R1 plus delta R2. But since I have chosen R1 and R2 initial values to be 0, the change in R1 is equal to its final point. The change in R2 is nothing but the final point. So the sum is also 0. Well, if you just sum them up twice, R1 final is equal to 1 meter. R1 final is 1 over 2 meters. So according to the outside observer, I moved half a meter in one direction. We already know that the cart just moved with the same magnitude in opposite direction, with the same magnitude. It's just minus half meter.
Versus displacement is now 25 meters.
Now half a meter. This R1 is the displacement, or delta R1. This is the displacement, which is R1 final minus R1 initial. We just chose the origin to be at the initial point, so R1 initial is 0. This is 0.5 meters. The displacement for an outside observer is half a meter. So if I'm staying here, I want to move to that point, which is 1 meter away. As I start moving in that direction, the car will start moving in the opposite direction. So when I reach that point, I will be just half a meter away from my initial point, according to him. Because I have on the reference frame on the car, which is not an inertial reference frame, I moved 1 meter in that direction, but that reference frame had moved half a meter in the opposite direction. So according to him, when he looks at me, what he will see that I have only moved half a meter in that direction.
The mass of the cart has a mean.
Well, let's see what will change if the masses were different. We started with the definition of the center of mass. Now, if the masses were different, instead of this expression, we should use this one. So it will change the displacement. The heavier the car, the less it will move. You see, this relation, this expression will just be m1 times delta R1 plus m2 times delta R2. This should be equal to 0. So if, let's say, m2 is very large, if the mass of the car is very large, then we need a very small displacement to compensate for my displacement.
Why do we need momentum? Why momentum?
Well, I mean, to say the least, the conserved quantities always makes our life easy. We already seen one example, the conservation of mechanical energy. We don't need to bother about what happens in between. We just look at the initial state of the object, initial position and the velocity, and the final position and the velocity. So by ignoring what happens in between, we can just look at these two things. The same thing will be true for momentum. For example, when we will be studying collisions, that will be one of the most important applications of this conservation of momentum. So when two cars collide, the forces that they exert on each other, we don't know. They are very complicated. There will be very complicated forces. But when we were driving the conservation of momentum, we didn't make any assumption on the nature of the forces. The only thing we used was they have to be action-reaction pairs. As long as there are action-reaction pairs, the momentum is conserved. So although we don't know what the forces are, so we cannot really solve for how the velocity or the position changes as a function of time, we can still say some general comments about what's happening, what will happen, what will come out. Also, this is one of the reasons why you can play pools. You know, the billiard balls. That's an application of the conservation of momentum. When you are judging in which direction you want to send your target ball, You are just adjusting the initial speed and the initial direction, etc. And those adjustments are just to make sure that the momentum is conserved in such a way that will make the target ball go in a particular direction. Of course, there is also the rotation part of the game, which we will study in a couple of weeks.
Game cool. When we shot a ball, it will try to move the table with accommodation.
It will?
Try to move the table also. So since it is center of command table and ball should be safe. But there is friction.
Okay.
Table, the ball will be exerted a force on the table.
Okay.
You'll try to move the table, but it won't move the table.
Okay.
That's the case. I just, this is the case.
True. True. But when the balls collide, I'm not talking about the momentum conservation of the ball and the table, but when you have one ball moving, it hits another ball. So you can say that the external forces are will be negligible, or their effects will be negligible during the collision at least. So we can still say what will the other ball do after the collision.
So we can say this equivalent is N1 plus N.
This one?
Yeah, and this.
Yes.
Can we say?
Sure. In which case? In the billiard ball case?
In this case. Same thing.
Yes, we can. Now, even if there are external forces, by the way. Now, this one will not be true, but we will be studying collisions on Thursday. Now, the collisions usually last a very short amount of time. And we had seen that the change in the momentum of an object, even an expanded object, will be proportional to the force times the time that that force exerts. Now, if there are external forces acting on your system, but if the collision lasts very short, then during the collision, since the time of the collision is very short, still the momentum will be approximately conserved, since the collision lasts very short, even if there are external forces. Like we will see examples where if you throw an object, a projectile, when it reaches some point, it will just explode into two. Well, there are external forces, but if the explosion takes a very short amount of time, the momentum will be conserved during the collision. Other questions?
Is there any amount of car of mass that distance
Can you repeat your question?
Arabanın bir kütlesi çok fazla yüksek olursa yer değiştirmesi doğru değil mi?
Well, if the mass of the car goes to infinity, in that case the displacement will be zero. But as long as these masses M1 and M2, they have finite values, the displacement will never be zero in the absence of friction. If you do this experiment, just go on top of a cart and try to move from one side to the other side, well, of course the cart will not be displaced because the friction will be huge. Now, if you want the car to be displaced, the force that you exert on the cart should be much larger than the friction forces. So if you try to run very fast, accelerate very fast, in that case the car will be displaced. But if you accelerate very fast, you have to pay attention to stopping also very fast before falling off the cart. But if you, let's say, if you take your cart on an icy day, okay, how many of you are from Ankara or from a snowy place? Okay, so you have probably already fallen down on ice, right? So what happens when you fall down with ice? Okay, at one instant you are standing up, at the next instant your feet are up, but your body falls back. Because since the friction force is very small, there are no external forces acting on your system, so your center of mass should stay where it is. There is no acceleration of the center of mass. If your feet go forward, your top part of your body should go backward. Or if you haven't fallen down, you will probably have lots of opportunity this winter. Other questions? Okay. Okay. We need to leave. So if you have questions, you can just come here. See you on Thursday.